Hey, welcome! Today, we're going deep. I mean, really deep. We're heading a mile underground to get a first-hand look at one of the most ambitious physics experiments on the planet, the Deep Underground Neutrino Experiment.
Particles 800 miles. That's 1,300 kilometers straight through the Earth's crust. No tunnel or anything. And our job right here in this cavern is to catch them on the other side.
But why? Why go to all of this trouble? What are we even hunting for? A mile underground with a beam of particles that can just phase right through a planet? Well, we're after one of the most mysterious, most elusive particles in the entire universe. Say hello to the neutrino. We call it the ghost particle for a pretty simple reason. It almost never interacts with, well, anything. To put that in perspective, right now, as you're watching this, about 10 billion neutrinos from the sun are zipping through your hand every single second. And yet, over your entire life, it's almost a guarantee that not a single one will ever bump into an atom in your body. They're literally everywhere, but they're almost completely invisible to us.
And studying these tiny little ghosts might just help us answer the biggest question of all. Why are we here? Are the very building blocks of you and me permanent?
This is where we get into something called nucleon decay. Nucleons are just protons and neutrons. And the wild idea is that protons, the core of every single atom in the universe, might not be stable forever. It's a key prediction of some of our biggest, most ambitious theories, like grand unified theories and supersymmetry. You might hear them called GUTS and SUSY. If we could find even one single proton decaying, it would be absolutely revolutionary. It would prove our standard model of physics is incomplete.
Okay, so we're hunting for two incredibly rare things: a tiny difference in how ghost particles behave, and a proton that might decay like once every trillion years. How on earth do you build a machine to see that? Well, you build a giant, super high-resolution digital camera for particles. This is the heart of the whole operation, the liquid argon time projection chamber, or a LAR-TPC. You can kind of see the idea here. A particle zips through on the left, leaves a trail, and that trail drifts across this huge volume to be read out by super sensitive wires. This technology is what makes DUNE so incredibly powerful. It lets us capture these stunningly detailed 3D images of particle collisions. So let's break down how this camera works. First, a particle flies through our vat of super cold liquid argon. When it does, it creates a quick flash of light and knocks some electrons loose, leaving behind this little trail. A whole array of light detectors sees that flash almost instantly. At the same time, a powerful electric field starts pulling that trail of electrons slowly across the detector. As the electrons arrive, they pass through 3 different planes of incredibly fine wires, each one capturing a 2D snapshot. And here's the brilliant part. We combine the timing from that initial flash of light with the data from those wire planes, and boom, we get a perfect, precise 3D reconstruction of the particle's path. It's really like a modern digital version of an old-school bubble chamber. Now you might be wondering, why go to all the trouble of using liquid argon? I mean, other huge experiments like Hypercameo Konde in Japan use enormous tanks of super pure water. And water detectors are amazing for counting things. They see these faint rings of light when a particle hits. But liquid argon gives us something else entirely. It's much denser. And instead of just a faint flash, we get a full, high-resolution picture of the particle's track. And that imaging capability is the whole ballgame. It means we can not just count events, but we can clearly identify what kind of particles were created and, crucially, throw out all the background noise. And let me tell you, throwing out the background noise is maybe the single biggest challenge we face. Because finding a single proton decay is like trying to hear a pin drop in the middle of a hurricane. This right here is the hurricane. Even a mile underground, we're constantly being pelted by neutrinos created in the atmosphere. This table gives you a sense of the problem. In just 1 year, inside a single one of our detectors, we expect almost 3,000 of these background events. This is the constant cosmic noise that we have to somehow filter out to find maybe one single proton decay.
And this is the pin drop we're listening for. It's a simulated image of what we think a proton decay would look like. I mean, just look at it. See how clean and distinct that signature is? The liquid argon gives us this beautiful, clear picture. Our entire job is to find this one specific, pristine event buried among thousands and thousands of messy background events.
So how in the world do we do that? We can't have people scanning millions of images by eye. So we turn to machine learning. We train a special algorithm. It's called a boosted decision tree to be an expert at telling the signal apart from the background. It looks at a whole bunch of features for each event. It checks the event's topology. Is it a clean 2-track event like we expect, or just a messy spray of particles? It checks the total energy. Does it add up to the mass of a proton? By combining all of these clues, the algorithm learns to spot the unique fingerprint of our signal with incredible accuracy.
So, you see, finding this signal isn't just a technical challenge, it's part of this huge global quest to push physics beyond our current understanding, what we call the Standard Model. And it turns out there are a couple of different ways to go about that. To really get DUNE's role, it helps to compare it to an experiment you've probably heard of, the Large Hadron Collider, the LHC. The LHC works on what we call the energy frontier. It smashes protons together with unbelievable energy to try and create new heavy particles. DUNE is totally different. We're on the precision frontier. We're not trying to create anything new. We're observing the particles that already exist with mind-boggling precision, looking for these impossibly rare events. You could say the LHC is a search based on production, while DUNE is a search based on observation. They're two totally different but complementary paths to the same goal: finding new physics. And as researcher Christoph Alt puts it here, looking for proton decay is one of the most powerful tests we have for these big ideas. Theories like grand unification and supersymmetry are super compelling because they solve some major puzzles in physics, but they make a key prediction that we can actually test. Protons have to decay. Finding that would be the smoking gun.
So just how sensitive is DUNE really? Well, our projections show that if we run the experiment and don't see a single proton decay, we'll be able to say its lifetime has to be greater than 1.3 times 10 to the 34 years. Now, that number it's almost impossible to wrap your head around. It's over 1 trillion times the current age of the entire universe. That's the absurd level of precision we need to actually test theories like supersymmetry, which predict lifetimes right around that number.
And this really brings us to the final and most exciting question. You've got DUNE on the precision frontier and the LHC on the energy frontier, both hunting for the first real crack in our current understanding of the universe. They are both closing in on a discovery that could totally redefine physics for the next 100 years. So, which one is it going to be? The raw power of the LHC or the patient, precise observation of DUNE? That's the race we're in right now. And honestly, whatever the answer is, the future of physics is going to be incredibly exciting.